Okay, we're going to start this next part with another gravitational problem, number 39. Number 39 talks about the astrology and the forces exerted by various planets based on their positions. And the first question, rather than reading this whole thing, is to ask the question, calculate the gravitational force exerted on a 4.2 kilogram baby by a 100 kilogram father that's 0.2 meters away at birth if he's assisting. So again, you use the gravitational, which would be G times the mass of the father, mass of the baby, divided by the distance between them. So that's going to be 6.67 times 10 to the minus 11 times the force of the mass of the father, which is 100 kilograms, the mass of the baby, which is 4.2 kilograms, and the distance between them, which is 0.2 meters squared. If you do the calculation here, you get 7.01 times 10 to the minus 7 newtons. Now that's why when you hold your hands out, your baby doesn't come flying towards you, because that force is really small. Now the second question is calculating the same force, except now it's due to Jupiter, which has its closest distance to the Earth at 6.29 times 10 to the minus 11 meters away. And we already know, or we can look up Jupiter's mass as well. It's the same formula. So it's 6.67 times 10 to the minus 11. The mass of Jupiter is 1.898 times 10 to the 27th kilograms. And the mass of the baby is 4.2 kilograms. And the distance now, given in the problem, is 6.29 times 10 to the minus, or times 10 to the 11, and that is squared. And this square of the distance is what makes the force of Jupiter not real influential on the child, because when you do this calculation, you get 1.35 times 10 to the minus 6 newtons. And then the last is, well, actually, that's it. And the next problem is problem number 40. Problem number 40 talks about the effect of planets on each other. The existence of the dwarf planet Pluto was proposed based on irregularities in Neptune's orbit. Pluto was subsequently discovered near its predicted position, but now it appears that the discovery was fortuitous because Pluto is small and the irregularities in Neptune's orbit are not well known. To illustrate that Pluto has a minor effect on the orbit of Neptune, compare it with the closest planet to Neptune, which is Uranus, I believe. So it says calculate the acceleration due to gravity at Neptune due to Pluto when they are 4.5 times 10 to the 12th apart, as they are at present. And the mass of Pluto is 1.4 times 10 to the 22. Now, it's the mass due to gravity. So now we use that gm over r squared. So this is 6.67 times 10 to the minus 11. And the mass of Pluto is 1.4 times 10 to the 22 kilograms. And the distance is 4.5 times 10 to the 11, and that's squared. And if you do that, or 10 to the 12th, it's 10 to the 12th, excuse me. And if you do that, you get 4.61 times 10 to the minus 14 meters per second squared. So that's a very, very small number. The second question is calculate the acceleration due to gravity at Neptune due to Uranus, which is the next close planet. And it's the same calculation, except now we're going to put in the mass of Uranus. So it's 6.67 times 10 to the minus 11 times the mass of Uranus is 8.62 times 10 to the 25. Uranus is a much bigger planet than Pluto. And it's a little bit closer as well at 2.5 times 10 to the 12th meters, which is squared. If you do that calculation, you get 9.2 times 10 to the minus 10 meters per second squared. So there's 1,000 difference between these two, actually 10,000 difference. If you divide, which is what they ask you to do in the next part, if you divide this number by this number, you find that the influence of Uranus is greater than the influence of Pluto by 20,000 times. And so, like it says in the book, the discovery was fortuitous. The last section we're going to work on, and I'll tell you that I'm only exposing you to these problems because I think you may see them in college at some point. I want to make sure you know that how to do them or how they work, is the satellites and Kepler's law. And the key to Kepler's law is the relationship between the radius of the orbit and the period of the orbit, which is given by this relationship here. And there's a table, 6.2, which shows various R's, various planets, various R's, and periods. And we will be using that table several times. And the first problem number 43, says that a geosynchronous Earth satellite is one that has the orbit period precisely 1 day. So the period of this satellite is 1 day, or 1 over 365 years. Now the reason I say that is because the table, such orbits are useful for communication and weather observation because the satellite remains above the same point of the Earth, provided it orbits at the equatorial plane in the same direction as Earth's orbit. So calculate the radius of such an orbit based on the data for the moon. So they want you to take the table, take the moon data, and the moon data says that R3 cubed over T2, over the period squared, is 1.01 times 10 to the 19th kilometers cubed over years squared. And that's why I said this in years. So if we use that and solve this for R is going to equal 1.01 times 10 to the 19th times T squared. And that whole thing is going to be taken to cube root, which is equal to 1.01 times 10 to the 19th times, and T now is 1 over 365 in years. And that number is going to be squared, and we're going to take the cube root of that. And so if we do that calculation, we get 4.23 times 10 to the 4th kilometers for the radius. 4.23 times 10 to the 4th. The next question says calculate the mass of the sun based on data for Earth's orbit and compare the value compared with the sun's actual mass. Okay, so we use the table again, table 6.2, and we get R3 over T squared, and that's going to equal 3.345 times 10 to the 24th kilometers cubed over years squared. Now there's another formula that you need in order to do this problem. And that other formula, which is in your book, is a derivation. that says that the r cubed over t squared is equal to gm, where g is the gravitational force, m is the mass of the planet in question, over 4 pi squared. Now, in order to use this formula, you have to realize that g here is in newtons and meters and seconds. And so numbers that you get out, you see this is kilometers and years, so you have to convert this from kilometers and years to meters and seconds, and I'll show you how to do that in just a second. So that means that this number is going to be equal to this. So if we want to calculate the mass, we're going to take this number times 10 to the 24. We're going to multiply that by 4 pi squared, and we're going to divide all of that by g, and that's going to give you the mass. But because of the difference in units between this and g, we're going to have to finagle this top part just a little bit. So let's take this 3.345 times 10 to the 24th, and we're going to have to multiply that by 1,000, because there are 1,000 meters in a kilometer, and we're going to have to divide or multiply by 1 year, and I just did I did the math here. I changed this to seconds rather than having a great big long string of numbers. And so this is a time, so this part's going to be squared. That's the period, okay? And this part is going to be cubed, okay? And so if we take all of that and then multiply it by 4 pi squared over g, which is 6.67 times 10 to the minus 11. Now the thing that makes this problem a little bit complicated is the fact that you have to put this in, and the fact you have to put this in to change the units around. But once you realize that, it's not really that hard to figure out. And you get 1.98 times 10 to the 30. And if you remember from our previous problems, that's pretty close to what we know to be the right answer. 45 is a very similar calculation, actually 45 and 47. 45, we have the question is find the mass of Jupiter based on the data for the orbit of one of its moons. And again, you take 0.00485. Now you're wondering why it's so small. That's because the moon is very small and it's very close to Jupiter. And so that's the calculation, and the distance r is 4.22 times 10 to the 8th, or 10 to the 5th in kilometers, 10 to the 8th in meters. And so you have m is equal to r squared over r cubed over t squared times 4 pi on the top here and g on the bottom. And if you put the numbers in, you get 4 pi squared times 4.22 times 10 to the 8th cubed over 0.00485 times 3.16 times 10 to the 7th. And all of this, that's the number of seconds in a year. All of this is squared. And this is multiplied by 4 pi squared over 6.67 E10, e to the minus 11, excuse me. I'm sorry for the background noise. The answer here is going to be 1.89 times 10 to the 27 kilograms. The last problem is very similar. This is astronomical observations of our Milky Way, and I'm not going to read the whole thing, but again, we do this the very same way. The first question, we have to calculate the mass, which is given as so many solar masses. So the mass is going to be equal to one solar mass is 1.99 times 10 to the 30, and it says that there's 8 times 10 to the 11th solar masses. So the Milky Way has a mass of 1.59 times 10 to the 42 kilograms. It also says that the radius is 6 times 10 to the 4th light years. So that's 6 times 10 to the 4th times the number we have for seconds in a year times the speed of light, which is 3 times 10 to the 8th. So the radius is 5.7 times 10 to the 29 meters. So you have this mass and this radius. If you rearrange this formula right here to calculate t, you get the following. It's going to be the square root because of 4 pi squared times r cubed divided by gm. If we use this as m, this is r, and put it in here, and g we already know, then t is going to equal 8.3 times 10 to the 15 seconds, because we convert to seconds, and then we can convert that back to years, or 3 times 10 to the 8th years. So the period is going to be 3 times 10 to the 8th years. And then part B just changes what the period is and asks you to calculate back to the mass. And I'm not going to, because of time on this section, so we have mass now, I'm going to go ahead and do this, is equal to 4 pi squared over g times r cubed over t squared. And now we have a new period, and if you do the calculation based on the new period, and the radius is still given, so if you put this number in as the radius and put the new period in, you get a mass of 3.04 times 10 to the 43 kilograms, or about 2,000 solar masses. So if you just change the period by the amount given, so if we put 4 pi squared over 6.67 times 10 to the minus 11, and we put in the new period, which is 5.7 times 10 to the 20 cubed, and the new radius, and the period, which once you multiply this 6 times 10 to the 4 years with the seconds, you end up with 1.899 times 10 to the 15 seconds. And when you do all this calculation, you get this number, which